In this video, we're going to present experiment 2, single stage compressor by group 3. Members are Wanting, Henry, me, Ilmam, Iman, and Kwok. There's 5 members here. So for introduction, this experiment studies how a single stage compressor converts mechanical energy into heat. The focus is on understanding how compressors increase the pressure and temperature of gas, especially air, during a single step compression process using sliding vanes. This process is crucial for industries like air conditioning and power generation. The experiment tracks the heating curve, showing how air temperature rises during compression. Careful data collection and analysis are key to understanding this energy transformation. As for the two main objectives are to evaluate how quickly a single stage compressor heats up, and the second objective is to analyze the steady state heat loss of a single stage compressor. That's 5 members. As for the scopes, the first one is the temperature T2 is recorded every 1 minute and stops when a constant temperature is reached. The second one is the adjust the outlet pressure control valve so the outlet air pressure remains at 1 atmospheric pressure (atm) at all times. The third one is the working fluid is limited to air only.
Okay, for theory and working principle. A single stage compression means the air is compressed in one step inside the compressor. When the air is compressed, its pressure increases, and because of this compression, its temperature also goes up. This happens because work is done on the air by the compressor, which adds energy to the air, increasing its internal energy. If the process were ideal and no heat was lost to surroundings, called adiabatic compression, the temperature rise could be predicted using a formula that relates temperature and pressure changes. However, in real compressors, some heat escapes through the compressor's wall, so the actual temperature increase is less than in the ideal case. This loss of heat means the compressor doesn't work perfectly and some energy is wasted. Understanding this helps to analyze the efficiency of the compressor and design better system. Okay, as the figure 1 here show the single stage vane compressor demonstrate how mechanical work is converted into pressure energy by compressing the air. Okay, compressor operation. The core of the system is vane type rotary compressor driven by an electrical motor, and the rotor inside the compressor is mounted off center in a cylindrical casing and contains sliding vanes that move outward by centrifugal force. As the rotor spins, these vanes trap air between them and the compressor casing. The working cycles involve the following steps: the air intake, which is the suction phase. Air enters through the inlet pressure control valve and passes through the airflow meter. Then, the air is drawn into plenum chamber 1 section where its inlet temperature T1 and inlet pressure P1 are measured. Okay, the compression phase. Inside the compressor, the air is trapped in spaces between the rotating vanes. As the rotor turns, these spaces decrease in volume, which compress the air, increasing its pressure and temperature according to the thermodynamic law. Okay, discharge phase, which is delivery phase, the high pressure air is pushed out into plenum chamber 2 delivery. Here, the outlet temperature T2 and outlet pressure P2 are measured. The compressor air is then released through the outlet pressure control valve. Overall, a single-stage vane compressor operates under steady flow (SSSF) condition where the temperature, pressure, and flow rate of air entering and leaving the system remain constant over time, as do the heat transfer and work rates across its boundary. Air is trapped between two sliding vanes on a rotating offset rotor, and as the rotor turns, the volume of the trapped air decreases near the outlet, compressing the air and increasing its pressure and temperature according to the ideal gas law. The compressor has one inlet and one outlet, acting as a control volume uh, with continuous airflow in a fixed space. Applying the energy balance for this open system, when negating changes in kinetic and potential energy. Allows calculation of the energy added to the air by the compressor. After shutdown, airflow stop and the compressor release heat equal to the net work it performed during operation, consistent with the energy principle. Here are all the equation that we needed: specific volume through flow meter, volumetric flow rate, mass flow rate, energy added to the air by compressor, power out of motor, and heat emitted from the compressor.
So for experimental setup, from the left hand side, we saw the inlet pressure control valve, which is the green color one, and airflow meter V in, and outlet pressure control valve, which is the red one, and the pneumatic chamber 2 delivery, and P2, which is the outlet air pressures and the electric motor. So for the right hand side, we saw that got the pneumatic chamber 1, which is the suction, and P1, inlet air pressure, temperature 2, outlet air temperature, and T1, which is the inlet air temperature, and the spring balance to adjust until the motor is between the two black line, and also the compressor. So for methodology, the first step is switch on the power. The second step is fully open the green inlet valve, so turn the valve anti-clockwise to open it. So the third step is record the initial reading for all the parameters listed in table 1. So the table 1 will show in the result, and use a tachometer. So the tachometer is the orange one. So point the tachometer towards this orange color, and to record the motor speed N. Okay, so step 4 is switch on the motor. So after switch on the motor, we set the compressor outlet pressure P2 to 1 bar gauge, which is the atomic pressures, by using the red outlet valve. So turn the valve clockwise to increase the pressure. So after that, we adjust the spring balance, which is the black color one, to ensure that the indicator on the motor is between the two black lines prior to recording any motor force value. So the image 2, we can see that the motor is already between the two black line. So the step 7 is to record the temperature of the outlet air T2 at 1 minute interval until two consecutive readings are the same. So after getting the two reading are same, so we must stop the experiment. So to stop the experiment, we should reduce the compressor outlet pressure P2 to 0 bar by using the red outlet valve. So turn the valve anti-clockwise to decrease the pressure. Okay, so the last step is to switch off the motor and the power. So the specific volume of air was calculated by using the gas law. Then the volumetric flow rate was found and used to get the mass flow rate. So by using the temperature, the energy added to the air was calculated. Next, the motor power was determined by using the speed, force, and lever arm length. Finally, the heat loss by the compressor was found by subtracting the energy added to the air from the motor power. So all the formulas that already stated in the theory. Okay, so the last step is a graph was plotted with the time on the x-axis and energy on the y-axis, so showing the energy added to the air rising and lowering off while the energy emitted as heat increased more gradually, illustrating the balance between the input work, useful energies, and heat loss during the compression.
Next is the result part. So from table 1 is a list of the parameter for the single stage compressor unit. We record all the initial data in this table. So for table 2 is the outlet temperature data over time. We record the temperature of T2 every 1 minute until it reached the constant value, which is 30 and 31 minutes. So after we obtain the data of table 2, we can draw the graph of a outlet temperature T2 theta over time, which shows the heating curve. So next one, we are going to calculate our HC and the QC. So all the formula has been stated at the left-hand side. So by using all the parameters we record in table 1, we can calculate our specific volume through flow meter, which is V naught, the volumetric flow rate V dot, the mass flow rate M dot, and the power of motor W dot. After we obtain all these data, we can calculate our HC and QC. So for HC part, so we take the example for 0 second, which is initial. So the T2 is 67 Celsius and the T1 is 28 Celsius. So we can obtain our HC. So for the QC at the time 0 second, so it is the power or out of motor minus the HC. After that, we can build our table 3, which is the data of specific volume, flow rate, and water power. So by using this data, we can calculate our table 4 data, which is data for energy added to air by compressor HC and the heat emitted from the compressor QC for each 1 minute interval. So this is the data and the result we get. From the table 4, we can draw two graphs. So which is the graph 2? It is a graph of energy added to air by compressor HC against time. And the graph 3 is a graph of heat emitted from the compressor QC against time. And then we comes to discussion, part 1, which discuss the shape of the graph. So this is the graph 1. So based on graph 1, it shows the relationship of outlet temperature T2 data over time. By referring to the graph, as time increases, the outlet temperature T2 also increases. The magnitude of the gradient of the graph will also decrease slowly until it reaches 0. Next is the graph 2. The graph 2 shows the relationship of energy added to air by compressor Hc against the time. By referring to the graph, as time increases, the energy added to air by compressor also increases. This is because the value of M and Cp are constant throughout the experiment, and since T1 is to the x Celsius, so it's also a constant, the magnitude of the T2 minus T1 increases as T2 increases. Besides, the magnitude of the gradient of the graph will also decrease slowly until it reaches 0. And then comes to the graph 3. Graph 3 shows the relationship between heat emitted from the compressor QC and the time. According to the graph before, Hc increases with time. Since Wm is a constant, therefore, when Hc increases, then the QC will be decreased. The graph also shows that QC decreases exponentially with the time until it reaches 0.
So as for the discussion tool, let's recall back from our energy table, which is the energy added to air by compressor at every 60 seconds, or we call it 1 minute. The energy is calculated, okay, and this is the results that we had from the previous results. So basically, it's going down at first, going down from the heat emitted from the compressor QC. Okay, for the HC, which is energy added to the air by compressor, is basically increasing. So from the results, as we can see, the energy that is being input to the system is represented by Hc, which is the energy added to air by compressor, as I mentioned, measured in watts, W at each 1 minute interval. This energy Hc indicates the work done by the compressor on the air, and leading to an increase in the air's internal energy, which caused the system, the air, to heat up. So from the table, from the images that we had previous slide, the Hc value in watts, as I said, is increased as time progresses. For example, at 0 second, the Hc is the 163 0.3125 watt. At 60 seconds, Hc is 217 watts, and at 120 seconds it's HC 259 watts. At the end, it's at 1860 seconds, it's the HC 640 watts, which is increases. So from the previous result, I say roughly result. This shows that the progressive increase in HC demonstrate the system heating up over time as more energy is continuously added by a compressor.
Discussion Part 3. Amount of energy loss as heat as compared to A. The work input to the compressor. The work input to the compressor was maintained at 1600 watts supplied by the motor. The heat emitted from the compressor to the surroundings, representing energy loss, was measured at 710.22 watt. The energy transferred to the air during compression was 163.31 watt, calculated using the enthalpy change and the mass flow rate of 0.00487 kg per second. The air entered the compressor at 28 Celsius and exited at 67 Celsius, indicating a temperature increase of 39 Celsius. The total energy input was therefore distributed between the heat loss and the energy added to the air. The analysis of the compressor's energy distribution reveals significant heat losses compared to both the work input and the heat added to the air. The work input to the compressor is 1600 watt, while the heat emitted varies between 232.85 watt and 710.22 watt over time. This means that approximately 14.55% to 44.39% of the input energy is lost as heat, with the highest loss occurring around the 0 second mark, 44.39%, and the lowest around the 1860 second mark, which is 14.55%. This is how we calculate the percentage loss as heat. The work input to the compressor is given as WEL equals to 1600 watt. The energy loss as heat is represented by QC. So at T equals to 0 second, QC is 710.2219 watt. So the percentage loss is 710.2219 over 1600 times 100% equals to 44.39%, and then for T equals to 1860 second, the QC is 232.8469 watt, and the percentage loss is 232.85 over 1600 times 100%, which is equals to 14.55%. Next, for part B, amount of energy lost as heat as compared to the heat added to the air. The experimental results show that a larger temperature difference across the compressor correspond to greater energy added to the air and comparatively lower heat loss. This implies that more of the input energy was effectively used for compressing the air, enhancing the compressor's efficiency. Hence, at higher temperature difference, the compressor operates more efficiently, as less energy is lost as heat and a larger portion contributes to the useful compression work. When comparing the heat loss QC to the energy added to the air HC, the results show even greater variability. At 0 seconds, the heat loss is 434.9% of the heat added to the air, indicating inefficiency in energy transfer during early operation. However, by 1860 seconds, this ratio improved with heat losses dropping to the 36.5% of the heat added to the air. This suggests that the system stabilized over time, though a substantial portion of energy is still dissipated as heat rather than being used to heat the air. So this is the calculation how we calculate the percentage. The heat added to the air is given by Hc. The energy loss as heat is Qc. So at T equals to 0 second, Hc is 163.3125 watt and Qc is 710.2219 watt. So the ratio is 4.349 equals to 434.9 8%. So at T equals to 1860 second, HC equals to 640.6875 watt and QC equals to 232.8469 watt. The ratio is 0.365 or equal to 36.5%. So basically, the experiment shows that the compressor loses less energy as heat QC compared to both the work input WEL and the energy used to compress the air HC. Initially, at 0 seconds, heat loss is 710.22 watt, equals to 44.39% of WEL, while the energy added to the air is only 163.31 watt, equals to 10.2% of WEL. As the system stabilized, efficiency improved by 1,860 seconds. Heat loss drops to 232.85 watt, equals to 14.55% of WEL, and energy transferred to the air rise to 640.69 watt, equals to 40% of WEL. Higher outlet temperatures correlate with better performance. For example, at 1860 seconds, when the air reaches 1081 Celsius, heat loss decreased to 202.85 watt, while energy added to the air increases to 640.69 watt. This confirms that the compressor works more efficiently at higher temperature, converting more input energy into useful compression and heating rather than was wasting it as heat. Improving insulation or airflow could further reduce heat loss and boost efficiency. Next, we move to safety procedures. First, we need to wear appropriate PPE. Glove, lab coats, and closed-toe shoes should be worn at all times to protect eye, skin, and body from compressed air bursts, hot surface, or chemical splashes. This is to minimize injuries from unexpected events because hot surface on the compressor can cause burns and moving parts can catch clothing, hair, or fingers, leading to cuts or fractures. And then we should not exceed pressure limits. We need to always monitor and keep within the maximum allowable working pressure (MAWP) of the compressor. Keep an eye on pressure gauge to ensure the system operates within the safe limit, which is in this experiment 1 bar. This is because overpressurizing the compressor can cause system failure, rupture, or leaks, damaging the equipment. Next, we need to report malfunctions immediately, stop the experiment and notify the lab assistant or lecturer if any equipment behave abnormally. Heat from the compressor combined with combustible materials can start fires. The pressure buildups can cause components to rupture or explode. And then we need to beware of hot surface. Compressor generate heat, so do not touch hot parts during or immediately after operation. And then we need to allow the compressor to cool before touching or servicing to prevent burns. Lastly, we need to inspect the setup. Check for any loose connection, leaks, or damaged component in the compressor and associated piping. Before connecting the compressor, make sure the power source is off and properly grounded. A safe and stable experiment ensure that we can get reliable data. Leaks, unexpected shutdowns, or unsafe operation can cause experimental errors or interruptions.
Okay, so for conclusion, overall this experiment focused on investigating how the heat is converted to work using a single stage compressor system. So the setup included a compressor driven by an electric motor with sensor for measuring inlet and outlet air temperature and pressure, airflow rate, and the motor power. So the goal was to understand the thermodynamic behavior of air as it undergo the compression, which inherently involves the heat generation due to the work being done on the air. So if the temperature is increased, so for example, the inlet air temperature T1 which is 28 degrees Celsius, the outlet air temperature T2 reach a maximum of 181 degrees Celsius at 13 to 31 minutes. So they already consistent, so we can start the experiment. So this increase of 153 degrees Celsius clearly demonstrated the significant thermal effect of air compression due to the energy input. So for pressure difference, so the inlet pressure vacuum, the P1 is 0.05 bar, the outlet pressure is P2 1.9 bar. So the difference, which is the 1.85 bar, pressure increases show effective compression. For power consumption, we can see that the electric motor input, which is the 1600 watt, and the mechanical power input, which is the 873.53 watt. So a large portion of energy goes into compressing the air and overcoming the system losses. So the dynamic profile observation, which is the heating behavior. So when T is equal to 0 minute, the outlet temperature is 67 degrees Celsius, and when the T is equal to 10 minutes, the T2 is equal to 140 degrees Celsius. When T is equal to 20 minutes, the T2 is equal to the 168 degrees Celsius, and when T is equal to 30 minutes, the T2 plateaus at the 181 degrees Celsius, so it's consistent already. So the heating curve show a classic as asymptotic behavior, which is the rapid rise initially, then a greater stabilization indicating the thermal equilibrium. So all above the explanation was supported by our energy graph where the heat added by compression increases over the time, and we can see that the second graph is the heat emitted from the compressor decrease, implying the less heat loss as the system stabilize. So dynamic behavior of the compressor, the first one is as the compressor heat out, the air temperature at the outlet rise sharply, especially during the early phase of the operation. And then the thermal equilibrium is approached after sustained operation, where the temperature gradient between the T2 and T1 become more constant. So the compressor effectively slightly drops due to the internal heat buildup, which increases resistance and energy losses. So this behavior follow a typical heating curve, which is the initial rapid rise due to the rapid work input and minimum heat losses, and the slowing growth as the heat losses to the surrounding balance with the input energies. And the last one is the steady state, when the temperature stabilizes, indicating thermal equilibrium. So if the pressure two, which is the outlet pressure, is reduced, so means that the less work would be required to compress the air, and the outlet temperature T2 would rise more slowly and reach a lower maximum, likely below 100 to 130 degrees Celsius, and the heating curve would be flattened, reaching the steady state faster due to the lower energy input and reduce the air resistance and decrease internal frictional heating. So this would improve efficiency and reduce system strength, but may not suit application needing high pressure output. So for the suggestion for improvement, the first one is insulation enhancement. So in order to reduce the ambient heat loss and obtain more accurate thermal behavior readings, the second one is to automate the data logging, use digital sensors and software continuously monitors and record the pressure, temperatures, and flow data. The third one is multiple the pressure sensor run by running the compressor at the various outlet pressure, which is the zero point 0.5, 1.0, and 1.5 bar, to understand the border performance characteristic. And the last one is real-time visualizations. So implement the real-time graphical plotting of temperature. We have the time for dynamic analysis.
So here are the list of reference we use to make this uh, result presentation. We have 5 reference that we use. That's all from us, group 3, and thank you.